Oops. Right, we are now going to talk about gravitational potential energy. Okay, what's wrong? Why is my screen acting so strange? It doesn't go full screen. What's happening? There you go. In full screen. Talk to you about energy, right? So listen up. In secondary school and in all the lessons till now, gravitational potential energy is always given as mgh, correct? Your very handsome work energy power lecturer taught you that, right? Asked you to prove that. Right? Very handsome, he's a nice guy. Oh shit, I'm recording this. But I'm going to disprove that now. What was the assumption? The assumption is that G is a constant, right? But what did I show you? It's not. G is not a constant across big ranges of R. So we need to learn this new way to represent energy. So until now, I've shown you force, field, and I'm going to show you energy. These three equations you must remember. Out of these four boxes here, the only one that's given to you is potential. Okay, the only one that's given to you is potential. But I'm going to teach you a way to remember all this in the next lecture in a very easy manner, okay, to guarantee that you can remember. So let's go. Gradient potential energy. Okay. The moment you have a force between them, there is a certain energy. Right? There will be a certain gravitational potential energy. Because why? If you let go, let's say that this is the basketball, it looks like the moon or smaller version of Earth. If I let go, it will fly towards Earth, getting faster and faster and faster and faster and land on Earth, boom, like that. Right? So you convert some energy to Ke. Correct? And what's the energy you convert away? It must be gravitational potential energy. Okay? It must be gravitational potential energy. So the definition is this. Let's ignore the first part first, but we look at this. The gravitational potential energy at a point in the gravitational field is the work done by an external force in bringing a test mass from infinity to that point. Let's look at the second half first. What does this mean? And notice this. If I want to bring an object far away from me, let's say my head is the Earth, right? Those at home cannot see, and this is the object. As it comes closer to my head, it will gain Ke, right? So the work to do to bring this object to my head without an increase in Ke, which direction is the force? Outwards. The displacement is inwards. So the work done by me is a positive or negative value. The work done by external force would be a negative value. So hence, you shouldn't be surprised that there is a negative value here. Okay? By definition, there must be a negative value because it's a work done by the external force to bring an object from far away close to me. It will always be in the opposite direction from the direction of displacement. Now, when I say far away, actually I'm saying infinity. Okay? And the other trick is this, is that we take infinity to have zero gravitational potential energy. This one is a mind warp for most of students. Why? Because we always take the ground as zero potential energy. Correct or not? We always take the ground as zero potential energy. But here's the mind warp. We change the direction, the perspective. We take infinity as zero. So what will you have as a graph? You have this thing. Okay, you have infinity as zero. And you have at the surface of R a certain gravitational potential energy. So look once again at R for a variable, capital R for the radius of the Earth. Okay, so there is a fixed value of energy, of gravitational potential that you possess when you're on the surface of the Earth. And infinity is zero. So then you say, Mr. Ho, does it What do you mean? Do you mean that I lose energy as I go further away from Earth? No, it's not true. Look at the direction. I now possess negative energy. To go far away, I must move upwards, right? I must move upwards in a trend line for energy. I must move upwards. To move upwards, I must have energy. I must add energy to it. Right? So to move further away, I must move upwards, which means I must add energy to it. Right? So this is the important point that a lot of students get confused over, right, for gravitational potential energy. So I say again, the 2 points are this. Infinity is 0. When you move further away, you're moving up the curve. You're moving to a higher energy. You're moving from this point upwards. This point upwards. Okay? Can? Do you see my cursor? You can see, right? So you move from this point outwards. So if you move from this point to infinity, how much energy must you add? If you are moving from the surface of Earth to infinity, how much energy must you add? You must add positive Gm small m over capital R, correct? So that it reaches 0. So same thing here, that's what I just said. So I'm moving on. Right? So the negative sign is the one that confuses most students, but you must learn to deal with it. Okay? Right, the nature is attractive because of negative sign. Gravitational potential energy is also a scalar. Right? It's negative bound by the gravitational fields of M. The sign is compulsory. And it is a scalar. Write down somewhere, it's a scalar. Energy is a scalar. Right, example 10. Consider an object, right, of mass m. Find the gravitational potential energy at A, B, and C. Oh, super easy. If H is much smaller than R, slightly above A only, B is only slightly above A, what will happen? Show that the energy is approximately mgh. And find the minimum energy to go from A to infinity and never to return. Right, so first part, let's go step by step. Energies will be like this. Boring. Huh? Just substituting the equation with certain values of R. Okay? A, B, and C, side by side. So you see a question like this in exam, you'll be laughing all the way, right? Because there's 3 points here and all use the same equation. So if you know the equation, it's super good. Right? 3 marks into the pocket. If you don't know the equation, then too bad, right? Oh, so you must remember this equation is very, very important. Right. Part B, they ask you prove that, part B is actually the harder one. Prove that the change in gravitational potential energy is roughly mgh. So there's a little bit of mathematics involved. To move from A to B, right? Which one has a higher potential energy? B has a higher potential energy, that's right. So you take UB minus UA. Right? B has a higher potential energy, so the change in potential from A to B is UB minus UA. It's an addition. Right? B, although it's less negative, it is a larger value than A. B being less negative is a larger value than A, so UB minus UA will give you this. Wow, see the mathematics and something for but it's okay lah. It's not really that hard. This just apply the equation from part A, apply the equation from part B, do the math, blah blah blah, you get this. Right, once you get this, you get this first, but you realize that if H is much smaller than R, right? This R plus H, as you can ignore this H completely, to become GMM times H over R times R. Let this be ignored. Okay, so this is approximation. But you realize that GMM over R squared, right? GM over R squared is just G on the surface of Earth. Then you get mgh. Can I say again? This part, when H is much smaller than R, this becomes H over R squared because this goes away. Multiply it, you get G, big M, small m, H, and R squared. You take out h, you take out m. On the left-hand side, what do you have? You have gm over r squared, which you know to be g. Right? So you proved that for small values of height h above a, this is the change in energy is as mgh. Lastly, to go from a to infinity, the energy required is this. Infinity is 0. Potential energy at A is negative gm over 1. 0 minus the negative of this gives you just simply this. Okay? Just nice, maybe. Right, so since we've talked about potential energy, I need to introduce to you the concept of escape speed. Escape speed, yeah? Listen carefully, yeah? If I jump, will I escape the earth? I will fall back, right? I jump higher, I'll fall back higher, faster, right? I jump super high, the hop, I also come back to earth, right? Why? I cannot escape earth because of the gravitational field. But there is an energy, there's a certain amount of energy where you can have to escape earth completely. This is what we call escape speed. That means you must have enough Ke to convert to gravitational potential energy and still have some Ke at infinity. You got that? No? Say again, so listen carefully, pay attention. Escape speed will tell you how much kinetic energy you must have, such that you can convert that kinetic energy to gravitational potential energy at infinity, and still have some Ke left, right? Or at least a Ke very close to 0. So what you actually mean is this: your kinetic energy is a simple conservation energy equation, right? Your kinetic energy must be more than the gain in GPE required. That means to escape Earth, the kinetic energy I have now must be slightly more than the potential energy I will have when I'm infinity distance away from Earth. Okay? That's the whole idea. Okay? So if you only just write this down and you didn't copy or note down what I explained, you will come back to this equation 3 months later and be like, what's going on, man? I hope you have copied down the explanation, or you will look at my videos again, okay? And relive the funny jokes. Escape speed. So the speed itself that pertains to that Ke can be then derived, right? Half mv squared equals gm over r. This gm over actually is from example 10c. You realize how it's built upon one another. Right? The previous teacher who did this actually did a good job. I only made some small changes to it. Rearrange, you get velocity becoming this. Okay? And that's your escape speed. Right? So your escape speed from Earth depends on what? Depends on the mass and depends on the radius. The larger the mass, the bigger the escape speed required. Hence, the more Ke required. The smaller the r, the bigger the escape speed required. Right? So it's a ratio of m over r. Okay? The ratio of m over r. Earth is pretty dense compared to the moon. It's more dense than the moon, so m over r, right, of Earth is larger than the moon. Okay? And again, also for Mars and so forth. So the escape speed for Earth is 11.2 kilometers per second. So if you want to run away from reality of Earth, right, all you have to do is drive a car faster than 11.2 kilometers per second. No problem. Cannot, it's per second, not even per hour, it's per second. It's very fast. It's very, 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 very fast. It's like traveling 11 kilometers per second. If I can do this with my 2.4, I'll be a happy man. Oh yeah, I shouldn't, because I would actually lift off from Earth and then never to return. Yeah, so I shouldn't. I know I can, but I shouldn't. Shh. All right. We have 3 minutes plus. Shh. Bear with me. I need to pack this because next week I'm going to give you a power pack lecture. So I need to squeeze a little bit. I'm going to introduce to you what is potential. Okay, we have done force. Today we have done field. We've done energy. I need to just show you what is potential. Okay, just show you what's potential. And then we'll conclude. I promise you, we'll conclude. How do we define field? How do we define field? Field is defined as, field is defined as force per unit mass. Very good. You look at these arrows. This picture is the culmination of 7 years of teaching experience, actually plus a lot more. About this one I come out on. But it's very good. You see, the definition of G is from this equation, right? Correct or not? Correct. So potential, how do you define? Use this equation, correct? Potential is essentially just the gradient potential energy per unit mass. Correct or not? Correct, No? Right? The gradient potential at the point is just the work done per unit mass by bringing external agent from that infinity to that point. It's the same definition you add in per unit mass. That's it. So I'm not making you remember more things. I'm teaching you how to remember one thing and apply it to many, many situations. The hard disk is fixed, but the RAM you can work on it. So this is the equation. Give me 1 minute. Okay. So if you look at this, what is the potential at infinity? Like potential energy, it should be 0. Very good, right? And you look at the graph, right? Draw the graph in. It's the same. I introduce it in the same manner as gravitational potential energy. But you can now imagine this. If I put a ball at where my cursor is, it will roll inwards. Correct? Potential is like a bit like height. Potential is a little bit like height. You put a ball in a high place, you roll to a low place. Right? All objects will seek low potentials. So same thing here. Right? You put something far away, it will go inwards, roll down the field, roll down the slope. Right? And that's it. We're going to end with this. You should look at example 11. Right? You should look at example 11 and try to answer. I'll talk about that later. And try to answer the question in the box, the next page. Right? With that, that's the end. I wish you had a great lecture. I'll see you next lesson, and that will conclude my gravitational lecture series. And you should start doing your tutorials also. Shh, hello. You should start doing your tutorials because I will be starting on the tutorial right after my last lecture. Okay? Ken, thank you. Bye-bye.